Okay. In the last class, we learned about the various MR, especially we focused on GMR, the giant magnetic resistance, and TMR, the tunneling magnetic resistance, which one are very important in modern spintronic devices. Actually, most of modern spintronic device based on the leading mechanism with GMR or TMR. So in this morning, we're gonna move on to next chapter. The title is spin dynamics. In other words, we wanna learn about the Landau-Ritz-Gilbert equation. In other words, it's LLG equation. Okay. So far, we learned about the how we can read the magnetic information in a magnetic device by the various MR, especially GMR are important, as I already pointed out. And that means we can convert the magnetic status to the kind of electric signal. That means we can read the voltage or current or resistance of the magnetic devices, which one depends on the magnetic status. So basically, such concept is applicable for any kind of magnetic sensors and any kind of digital information strategy. In a digital information strategy, can be magnetic hard disk drive or magnetic random access memory or magnetic tape drive and many kind. So most of digital information strategy is based on two stable energy state. Let's say this is a set 1, this is a 0, then we can form the binary data. And the requirement of the digital information is such a very stable two binary state. If the state is not stable, that means the stored information can be destroyed. But in other words, we need some kind of mechanism, move on, change the status from state 1 to the other one. So we need some kind of mechanism to overcome this energy barrier. So far we learned about the reading. And now I want to talk about the writing mechanism, especially for the magnetic devices. Yeah, in magnetic devices, the most simple and widely used technique is magnetic field. We already learned about that. With applied magnetic field, we learn how the magnetization switching occurred. And I already mentioned several times about the spin transfer torque, in other words, STT or SOT. Those two are very similar. And this STT and SOT are very important in modern spintronics. And there are something more like a voltage controlled magnetic anesthetic technology called VCMA. Yeah, maybe we can skip this part. Anyway, so before learn this spin transfer torque and spin orbit torque, we need to understand spin dynamics. Yeah, the spin dynamics on the external, maybe it can be magnetic field or STT or SOT. They are very common. We already learned about the Stone-Alpers model. So please remind that the Stone-Alpers model. And this one is a kind of static solution. Yeah, here we don't know, we cannot understand what's the meaning of these static solutions, but compared to LLG equation, this Stone-Alpers model, we call this static. That means we found the local energy minimum for given external disturbance. That means this field. So we can obtain the MH curve. Please remember that. But in this calculation, there's no time dependent. Yeah, the true motion of the magnetization has a time dependent, but in this calculation, there's no time term in the equation of storm alpha model. They are just energy equations. And there's no role in a damping. In storm alpha model, we cannot see any damping mechanism, which one is important in real spin system. And why this damping is not occurred? Because we are in this storm alpha model is something like this. If you set, if you have some ball, and if you pass the ball to the vertically, you know the result. They going up and going down, and finally they came here. Storm alpha model implies they know the initial state, and then they know the final state. They don't deal about this trajectory. But in an LLG equation, they are talking about the whole trajectory of the ball. So in a storm alpha model, is energy equation. So what we know is with the if you're sending the ball to the V0, then the height of the maximum height is given by this equation. That's all. But in this case, we solve the time-dependent solutions. So we can find the position and the velocity of each point at a given time. So especially in a spin system, the time scale is the sub-nanosecond scale. Yeah, we will learn why the spin response is order of second or sub-nanosecond. And we already learned there is some precession motions in with the external magnetic field, and the damping is important in this LLG equation. And also, this LLG equation is very basic equation to describe the equation of motion of the spins, and mathematically it's kind of ordinary differential equation. So that means there are many ways to solve it. And also, I mentioned that micromagnetics, which one is widely used scheme of the numerical way to solve the magnetization reversal. And the LLG equation is a basic equation of this micromagnetics. Okay, so actually this LLG equation was developed a long time ago. The LL stands for Landau-Ritz. You know, they are very famous physicists in Russia, and they developed called the LL equation. And Gilbert added some additional term to describe the damping part more precisely. So this paper was published long time ago here. Yeah, something here. And fortunately, IEEE decided published this paper again at 15 years ago. So you can easily find the paper in IEEE Transaction on Magnetics journal. Okay. So let me start. Why the LL or LL education are important in understanding the magnetic dynamics. I already mentioned LL or LLG equation are the master equation. That means they can apply, they can use to understand the spin dynamics in most of the case. And as you see here, the equation looks very simple. This equation implies if we have some effective field, we can find the trajectory of the emancipation dynamics. And this effective field is determined by the total system energy here. If we have an energy equation, and if you take the gradient, the emancipation directions, then you can obtain the field. Here, just to remember that the Gman energy is the effective field. So that means if you have energy here, if we're taking the gradient, the direction of the m, then we have a kind of field. So it's somewhat similar to the force it's given by potential, the gradient of the potential energy. So if you have a different energy, let's say the anisotropic energy, if you're taking the, sorry, maybe, yeah, if you use the anisotropic energy to obtain this field, we can obtain effective anisotropic energy. And if you play with the exchange energy, if we have a exchange energy, external effective field corresponding to the exchange energy, and so on. So any kind of energy can be converted to the external effective magnetic field. That implies if we have some energy profile, the function of the emancipation direction. So please keep in mind, this is not the position, this is the direction of the emancipation. And the energy will be depends on the emancipation direction. Just to simply imagine the anisotropic energy. Anisotropic energy has a, let's say, this form. Here the cosine, the theta means the direction of the emancipation. So they have a energy minimum at theta is 0. So this energy equation implies if we have some kind of deviation from the ground state or the stable state, there is some restoring force. It's same for general equation for the force and the gradient. So this restoring force is a kind of a field. So the emancipation come back to the lowest energy point. So that's the concept of the effective field. Okay. And this second term is called the damping term. We're going to learn about this more details today. So to understand the concept of the effective field, is there no problem? Okay, let's move on. So let's back to the spin precession again. We already learned about the magnetic precession motion. If we have an external magnetic field or effective field, the spin has a precession around the effective field direction. Yeah, let's recall our previous lecture note again. Yeah, if we define the magnetic dipole moment with the current loops, with the rectangular one or the circular one, we already learned the magnetic moment of the this circular loop, current loop, is defined by the area vector. And as a result of the total torque, we already learned this equation. So the precession motion is easily understandable for the classical magnetic moment. And in a Raman precession, the magnetic moment M, the unit must be ampere meter square. Is the current multiplied by area is related to the rotation of the electrons or orbital motion. Or angular momentum. Okay. So we can connect the magnetic moment to the angular momentum, which one is called the gamma. The magnetic moment is proportional to the angular momentum. Here, the magnetic moment of the circular motion of electron, here is the area, here is the current. And this is the angular momentum of the electron, of the velocity v0 and the radius of r. So we can calculate the gamma, which one is the proportional constant between the magnetic moment and the angular momentum. Yeah, with the simple math, we can find this result. Okay, because v0t generate 2 pi r. So we can obtain this number, and this is electron charge and electron mass. So it's very fundamental constant. And let's calculate this number. So we can put the electron charge and the mass. We can obtain some number. And please take a look. The unit of gamma here is coulomb divided by kilogram. And from the definition of gamma here, this is okay. Here, gamma is L over M. So this is the unit of ampere meter square, and this is the angular momentum. So here, so you can easily check it out. The M square can be dropped, and angstrom is nothing else but coulomb per sec. So sec is dropped. So we only have a coulomb divided by kilogram. The unit of gamma is rather important, but the coulomb divided by kilogram doesn't make any sense. So let's start again here. The unit of gamma is start from the kilogram per coulomb per kilogram, and actually this is the more physically meaningful representation of the unit of gamma. Here, the Tesla unit of Tesla is Newton divided Coulomb meter per sec. You can obtain this result from in this form. The left-hand side is unit of Newton, and this is Coulomb, this is meter per sec, and B is Tesla. So you can obtain the Tesla unit here. So you can insert to here, you can obtain this form. And the Newton is kilogram per meter per sec square, because this is MA, the mass multiplied by acceleration. And then with this form, you can find this one is dropped, and only coulomb per kilogram is remained. Then why this form is important? Yeah, if we multiply the gamma with the field, it turns out 1 over sec. Then, in other words, this is the unit of the frequency. So, if we have an external field, B or maybe H or M, they are all related to the field unit. But the gamma can be, if you multiply the gamma to here, any field-like term, we can obtain the frequency, the time scale, the inverse of the time scale. Or if we working on the quantum mechanics, if we multiply the h bar to the omega, we can obtain the energy. So this gamma is kind of a magic number. You can convert field to the frequency or energy. So this unit implies if we multiply the gamma with some field term, we can obtain 1 over sec. So please remember this unit. And this number can be changed depends on the field unit. Sometimes people use the Tesla, sometimes people use the ampere per meter, sometimes Westel. So all this the field dependence, gamma has a different number. So that's the little bit confusing part for the beginner. Okay, so let's recall again spin. So far we are talking about the motion of electrons, which one is angular momentum. But please remember that we play with the spin, which one is intrinsic property of the electron, and spin is kind of angular momentum. So we can distinguish them. This is spin angular momentum, and the previous one is angular, the orbital angular momentum. This orbital angular momentum is related to the orbital motion, but the spin angular momentum is intrinsic angular momentum of the electron. And those two are coexistence in electrons in a metallic system. But sometimes this angular contribution is not so important. So many times we play with about the spin angular momentum only. Okay. And the magnitude of the spin angular momentum is here. So this is called the Bohr magnetron. And actually this is gamma H bar. This is the gamma. Okay. Okay, so then classically we already learned about that. There's some kind of a precession with the external magnetic field. If you have a magnetic moment, they have a precession motion. This is purely classical one. Let's think about the quantum mechanics. You know, Heisenberg equation of motion for a given Hamiltonian H, that is given by this form here. A is kind of physical observable. So in the left-hand side, the time derivative means if you solve this equation, we can obtain the motion of the observable A. Okay. So let's begin with the very simple case with the Zeeman energy. So that means the Hamiltonian is given by this form. Actually, this is the magnetic moment. And we know the commutation relation of the spin operator. Okay. And from this Heisenberg equation of motion, we can replace A by the S spin S. And in the right-hand side is commutator to the spin S with the Hamiltonian H. And Hamiltonian H is here. And this is we assume the HG field. So this is inner product. We have only SG and HG. And if you substitute this expression to here, we can obtain the commutation relation to here with the HG. And this commutation relation is there's something here. Okay, so the S vector is Sx this form, and this commutation relation is actually yeah. Okay. If we have here Sx, comma Sg with this commutation relation, we can obtain Sy IH the minus sign. Okay. And S and G we have it should be minus sign. And sorry. Yeah, if we are using this commutation relation, we can obtain something here. So yeah, if we have a Sx here, with a minus H bar Sy and Sy Sg is plus H bar Sx, something like this. And for the Sg should be 0. So with this relation, we can obtain this result. And this term, if you Hg back to here, this is nothing else but the cross product between the H field and the S vector. Okay. And the spin momentum, this one, is related to the magnetic moment here. So we can rewrite this one to the magnetic moment. Okay. And we are using this relation, the magnetron is gamma H bar. So from this relation, this is actually the same form of this one. Okay, so this precession motion is not only for the moment based on the orbital angular momentum, but it's also applicable to the spin angular momentum. So this is kind of general form. Doesn't matter. This is the orbital angular momentum or the spin angular momentum. Okay. So if we know the effective field, we can understand the motion of spin. And let's back to the meaning of the effective field again. So I already explained the external, the effective field is determined by the gradient of the total energy, the gradient. And this is somewhat similar to the gradient of the potential energy is converted to the force. Yeah, this is the simple explanation about this meaning. In the right-hand side, this is the equi-height map. So if we have such kind of mountain, we have such kind of the top view maps, and the gradient means if we have a narrow gap here, then we have a large gradient. So this gradient implies the acting force on the on object, this mountain. Or if we think about this mountain is the potential of the system, you can easily find if you have some mass here, we have such kind of force, or if we have a mass here, they have such force. Or if we have a ground state here, stable point, if we move back this object to here, there is some kind of returning force. This is the kind of effective force, effective field. Okay. And so far, we are talking about the precession motion. And from now on, I'm going to talk about the damping. Before we move on to the damping, if you have any question about this precession motion, okay. How about the other student? Are you guys okay? Okay. Yeah, let's think about the damping system. So somebody raised a hand. What happens? Who did it? Any questions? Okay, so that's the damping part. So in mechanics, when we learn about the mechanics, we are starting with the frictionless case. If we have a acting force, then there is a motion. And there are many examples of the frictionless. Okay, but the truth is, the friction is always exist in nature. So the problem is getting more difficult. So we learn the precession motion, which one is frictionless. But in a real nature, we always think about the friction. So without the friction, the magnetization is precessed around the external magnetic field. With the friction, the magnetization direction is along to the field direction. Here, please remember that without friction or without damping, magnetization as a just precession motion, they never go to along to the field direction. That's a kind of counterintuitive to your understanding. Many students think if you apply the magnetic field, the magnetic moment must be aligned to the field direction because of this energy equation. Yeah, that implies magnetization direction is aligned to the field direction as a lowest energy. But if you start in this point, let's think about that. The energy of this state is not the energy minimum, something here. Because the field direction is not the same, the magnetization direction is not aligned to the field direction. So in this case, energy is, and in this case, this angle theta is not changed during this precession motion. Then how we can go to this energy minimum? We need some process called the energy dissipation. We should extract the system energy from this energy to this energy. So this is not the same. So that implies we need to take out some energy from this magnetic moment to arrive the ground state energy. If we don't have such kind of energy dissipation path, there's no way the magnetization can align to the field direction. So that kind of energy dissipation mechanism is called the damping or friction. Okay. Just imagine if we have a frictionless surface here, and if we apply the force, then the velocity of the this object is going to infinite. That's not quite correct because we have always friction. It's something like that. If we don't have a friction or the damping, the magnetization is precise forever. But with damping, they are going to the field direction. And there's many origin of the damping. Most easiest categorize is intrinsic one and the extrinsic one. But the details of the damping mechanism is too much in this class, so I'm gonna skip it. Okay, so just to think about the origin of the friction in fundamental physics. Yeah, the physical origin of the friction is surprisingly, it's not very well defined and not very well understood. But just what we understand is if we have two substances touch each other, and there's some kind of interaction can be exist between these two surfaces. And basically, such kind of interaction is based on electromagnetic force, like a Van der Waals force or Coulomb force, and any kind of force can be described by this electromagnetism. And this kind of friction force is usually we obtain by empirical way because they involve too many particles, so it's impossible to calculate by the first principle. So basically, this friction force convert the kinetic energy to thermal energy or heat. So that, in other words, that means we can, this friction provide the way to dissipate the energy to the environment. It's the same thing happens in our damping system. Then how we can describe that kind of friction? Just to imagine the falling body. If we have a mass m and gravitational force g, the acting force is mg. And we can obtain easily the position and the velocity as a function of time. As I already said, if we have no friction they are going to infinite by the time increasing. But physically, that is not quite correct. So if we introduce the friction force, in first case, the friction is proportional to the velocity v. Then we can easily obtain the terminal velocity of them. Means when the gravitational force and the friction force are balanced, then the total force acting on this mass m will be 0. So at that point, there is no change of the velocity. So that's why we call the terminal velocity. And we can solve this result very easily. And in sometimes in like some inside the liquid, the motion of the mass m generate the force which one is proportional to the v square instead of the v. And they generate the terminal velocity also in this form. And in this case, they are easily reached the terminal velocity very fastly. So anyway, depends on this damping mechanism or the friction mechanism, they can be proportional to V or they can be proportional to V square. But in many cases, many friction force can be described by the linear or the square term of the V. And let's recall the Ohm's law again. The Ohm's law, if we think about the microscopic Ohm's law, we have such a relation. In this relation, the microscopic Ohm's law is closely related to the, this relation, this macroscopic Ohm's law. In this derivation, we assume the friction force to the linear of the velocity of the electron. If we have a V square term, the Ohm's law is quite different. So that means this linear friction model is quite good to describe the motion of the electron inside of the conductor. Yeah, then why they should be linear? That's the very difficult question. And if we solve the Boltzmann equation, which one is statistical problem of the electron, the particle motion, then you can obtain such term. Anyway, so let's think about the first harmonic oscillator. In this equation of motion of the first harmonic oscillator, we also think about this damping term. This dx dt is nothing less the velocity. So that means the damping is also the linear to the velocity v. So we can obtain such a damped harmonic oscillator, the first harmonic oscillator motions. Okay. So in a spin system, damping mechanism is kind of a friction force. So the kinetic energy is converted to the thermal energy or heat of the environment. So damping in the spin system plays very similar role. If you have a precession spins with the excitation of the external disturbance, they generate the spin wave or eddy current or lattice vibration or strain. That means spin wave means the generate the magnon. And the eddy current means kind of conduction electron motion, and lattice vibration is related to the phonon. So all those processes required the energy dissipation. So by the damping, we can make such kind of phenomena. Okay, so let's back to the equation of motion of spin again. Yeah, let's back to the without damping system. The manipulation dynamics can be described by the classical equation of motion of the rotating body. Here, this is the time derivative of the angular momentum, and this is torque. Okay, and we can replace this angular momentum to the spin momentum S, and the time derivative of S, the angular momentum, is related to the torque. And also, we already know magnetic moment of the spin is given by gamma S. Here, the gamma is negative value because the direction of the magnetic moment of the spin are opposite direction to the angular momentum of the spin. Okay, so the torque of the magnetic field is given by M cross H. And we already know this Friesen equation. Here, the H field is came from the effective magnetic field definition, or in this form. Actually, this is the same form. Okay. And this U is the energy of the system. Okay. And we assume the magnetic moment, the magnitude of the magnetic moment are constant. So it's also the only the function of the rotation of the magnetic moment. Okay. So let's think about let's introduce the damping term. Here we introduce called the Rayleigh dissipation function. The friction force is proportional to the velocity of the dynamic variable of the system. Yeah, this is the nothing as the velocity. That's why I explain there are many systems as a friction force proportional to the velocity. Yeah, if we just gave this equation, you may have a problem to understand. But now I introduce many similar examples, so you may observe this linear behavior, linear dependence of the friction force to the velocity. And let's say the proportional constant is called eta. Okay. And the energy of this expression can be described by this relation. This is somewhat half of the eta velocity square. Okay. So don't confuse. This is the energy equation. This is the force. In a magnetic system, now we are talking about the motion of M. So dynamic variable Q is actually M, and Q dot is M round M round T. So we can replace the friction force in this form. Okay. And in a Lagrangian of the system must be function of the magnetic moment and the time derivative of magnetic moment. It should be such functional form. So it doesn't matter details of this form. You can build up the Lagrangian equation by the derivative, the m dot, and we can take the time derivative, and we can take the variable variation to the m, okay, and the frictional force term. And this Lagrangian is given by the kinetic part and the potential part. So let's substitute this one to here. In this Lagrangian, if you insert t minus 3 here, okay, then the t term, the kinetic term, is same to here. But the potential term, potential is actually the function of the magnetic moment, not the velocity. So this term gives a 0. So we have only remaining term for the potential energy, this term. And this is nothing else but effective field. So we have an effective field here. Okay. Okay. So if we compare to the undamped system where this term is not exist. So that means the role of this term is nothing else but replace the H effective field is this form. So we can replace this effective field with the damping with here. Okay. So if we rewrite this equation to here, we can obtain equation of motion of the LLG. So here the damping constant alpha is defined by eta gamma divided by ms. This is the called equation of motion of the LLG equations. Okay, so then what is the meaning of this damping term? Let's back to this precession motion. Here, this is the M cross H. M is here, H is here. We have a cross product between them. Then the direction of M cross H effective is this tangential direction. And this is actually the variation of M. So dm dt is this direction. In a top view, if there is some precession motion, then this direction is dm dt. Okay. And the cross product between this is generate this direction and this direction, the cross product between them. So the torque, the damping term generate this kind of torque. Okay. So here. Damping torque generate the torque direction to the field direction. So that's why we have a finally aligned magnetization to the field direction by the damping. Okay. So the important thing is the damping torque, this torque direction is always perpendicular to the M and the dm dt. So they are always pointing to the energy minimum direction, means to the field direction, the aligned to the field direction. Okay. So, actually, we are talking about the equations, but there is some another equation called the LL equations. In the LL equations, we have a little bit different form of the damping, the energy dissipation term. But this M cross H effective will generate very similar result to this term. They're a little bit different, but the damping is small. They are almost equivalent. So these two equations can be converted. Okay. So for example, you can easily convert from L equation. You can derive from L equation to L equation, or vice versa. This is the homework for homework. How you can convert these two equations. Actually, small damping, LL and LG are identical. But if the damping constant is getting larger, they are not quite correct. They're not exactly the same. But the damping is usually very small, so physically, those two equations are almost identical. So in this equation, this is the comparison these two equations. We can convert L equation to the LLG form. We can obtain this relation. And here the gamma value is changed from this relation. That means if the damping constant alpha is small, then gamma star are almost identical to the gamma. So that means if damping is not small, then they are not the same. So this gamma star determine the damping frequency, the precession frequency. So that means if the alpha is changed, the precession process frequency can be changed in this equation. Then what is the correct one physically? Unfortunately, experimentally, it is not easy to determine the difference because the damping term is always 0.01 or maybe 0.1, something like that. So that means they generate only 1% error or 0.01% error. Experimentally, it is very difficult to distinguish them. So in the sense of the experiment, they are almost identical. Okay. So in order to understand the spin transfer torque, I said you need to understand the LLG equation here. But in a spin transfer torque, we have an additional term. Okay. So I'm gonna explain why we have such an additional term, which means the physical origin of the spin transfer torque. And let's assume this term can be exist. Then what happens in a spin dynamics? To understand the macro spin behavior of the with the spin transfer torque, you should solve this LLG equation with STT term. And also, in a real system, it's not can be described by the single spin model. We need some of the small spins or ensemble motion. So that means we need a lot of spins, the summation of these all equations. That means we can call them micromatic studies. That's what we will learn in the next class. For questions, any questions? By the way, for the offline class, the university announced that they delayed the offline class. As you know, the session is changed during last weekend. There are, it is applied, but there are many new impacted person appeared, especially for the young student. So we're gonna delay the offline class again. Yeah, it is time for the questions. Please ask questions about this LL or L educations or dampings. Okay. The spin wave is kind of fluctuation of the spins. So, yeah, how can I say? Yeah, actually, the spin wave can be generated without damping. It's kind of, just think about the water wave without any viscosity. And eddy current is quite different mechanism. Eddy current implies they wanna generate current to how to say, compensate uh, the change of the magnetization is kind of electromagnetic problem. So, for example, if we have a conductor inside of the magnetic field, if they are moving fast, then there is some kind of induced current inside of the conductor because of the Faraday effect, Faraday law. Then the eddy current occurred to suppress such kind of effect because of the Lenz's law. So it's a little bit different mechanism, totally different mechanism between the spin wave and the eddy current. But maybe I wrote down made some misunderstandings in my lecture note. Yeah, this is the result of the. I'm sorry. Yeah, with the excitation of the external disturbance, like external magnetic field or any kind of things, they can they can excite the spins from the ground state to the excited state. And then they should back to the ground state by dissipation of the energy. And there are many passes of the energy dissipation, and that's what I'm saying. The generator spin wave or magnon, but without damping, they can survive forever. But with damping, they are going down to the ground state again. And the eddy current also generates the Joule heating. So that's the good source of the energy dissipation. And lattice vibration implies also generate of the phonons of the your system. And with the mechanical damping, they lost their energy. So that's also good energy dissipation source. Okay. More questions, please. Yeah, do you have any question? Yeah, the question during this class is very important to your grading, so please don't hesitate to ask any questions. Good questions. Yeah, I said the education can describe most of spin dynamics. So, yeah, I'm not 100% sure, but there is other equations called what's the name? Yeah, for example, in nuclear spin dynamics, people using different equations, and yeah, they have a little bit different form. So I'm not 100% sure this education cover the whole area of the spin dynamics, but for the melting material, especially for the spin harmonics materials, the LLG equation is good enough, but I'm not 100% sure they can cover all equation of the spins. So the strain means if we give a force to the material, then the length can be shrink down or expanded. That's what we call the strain. So the lattice vibration implies there is some kind of local strain. Okay. Any question you may ask by the Kakao Talk or email. Please don't be late. No. The variation of the crystal structure is not the same the strain. This is kind of phase transformation. That's not the strain. Strain implies okay. If we have an external force, we have some, let's say, lattice constant, then there's some kind of linear behavior. But if you give too much force, there can be some deformation, let's say, some sudden jump. I don't know what's the correct expression, but the crystal structure change is quite different story. Don't confuse it. Actually, if we have a cubic structure, for example, simple cubic, and if we have a certain amount of stress, let's say this direction, and the lattice distance can be increased a little bit. So generally in this case, this distance, let's say this is A and A, but in this case, A prime, A double prime, they are not the same. So in this case, we cannot say this is a cubic. This is kind of a, what is that? Yeah, there is some distortion of the lattice, and maybe you can call this is the crystal structure change. Because in this case, this direction and this direction are physically same in this case, but in this case, this direction and this direction are not equivalent anymore. So in this case, the many physical properties can be changed. For example, there is some additional anisotropy with the specific directions, but such a strain effect is kind of a statical one. But here the strain implies means time varying one because of the motion of the spins. So it's a little bit complicated situation. Okay, then yeah, if there's no more question, let's close today's lecture. And next Monday, I'm gonna talk about the spin. Okay, bye. 잠깐만.